Okay, welcome back. I hope you're all well rested after the break. I certainly am feeling a lot more energized. So today we're gonna get back to these B-IFSs, the coding map, its construction that we need to do. There's a theorem, which I'm calling the Hutchinson coding theorem and so on, that basically gives certain properties for this coding map, and that's going to be important later as well. Before we go into this, let me just mention 4 items. First, I've updated the syllabus. I've just changed the scheduling a little bit. Initially, we had 4 weeks of invariant measures at the end of the class. So now it's 3 weeks, and then so that we're doing 1 more week for we're dealing with topological dynamics and so on. So that's one. Second, I've uploaded the specification document for the final report and presentation. I'm going to go over it on Thursday, but before I did that, I thought it would be a good idea to let you guys know. Have a look at it in case you have any questions and so on. It's not, again, I did my best in terms of how specific it is, but again, it's sort of like not as specific as I would want it to be. So I want to give you guys some time to sort of go over it and think about, you know, what is sort of confusing perhaps. And then on Thursday, we're going to go over the document. Third, so at the end of the class, we're going to have, you know, in week 15, we're going to have presentations. So most of you answered, replied my email, but some of you still haven't. So I sent an email about the order in which you would want to sort of present. Please respond to that. And fourth item, of course, is that on Thursday we have Barnsley himself giving a talk. It's going to be a Zoom talk. And I would appreciate it if you could let other people know, people around you that you think might be interested in these kind of things. Okay, so these are the 4 items that I wanted to mention. Any questions about these so far? Yes? Is the talk also going to be recorded? I hope so, yeah. I'd like to be in attendance if I can. Yeah, we talked about it. So I corresponded with Professor Barnsley, and he said, okay, insofar as he can do some, you know, corrections and stuff like that. So it might become available at some point. Okay. I'm not saying immediately because, you know, editing takes time and so on. But that's it. Okay. So let me remind you the setup. We have a B-IFS, right? So that means that we have finitely many contractions acting on a complete metric space. I'm going to abbreviate by L the maximum of their Lipschitz constant. This is some number that is less than 1. It's so that it's faster to write things down. I'm going to have a shift space, right? So this is a space of one-sided shifts with symbols 1 to n. So these 1 to n, these symbols correspond to the indices. Okay, and then I'm going to denote by A sub w the unique attractor of the B-IFS W acting on X. What we want is this. We want a coding map, something like a conjugacy, phi, that's going to depend on W, of course, from the shift space to the attractor. And we want this function, we want this coding map, this function to be nice. We're going to discuss, we're going to spend pretty much all of today, and maybe on Thursday as well, some of Thursday as well, the properties of this. And I introduced last time, before the break, this cocycle. I said this is like a gadget that people use all the time in dynamics. I didn't sort of go too much into detail as to what this does, but ultimately this coding map is going to be related to this cocycle. So what does this mean? So it's a function from the shift space times the integers. Maybe I should be more specific. It's a cocycle, what people would say, over the shift. Cocycle over shift. over shift dynamics. So the way you should think about this is that somehow you're taking this shift, and the shift dynamics is sort of like this fast dynamics. That's sort of like the heuristic. And that fast dynamics is driving the iterated function system. That's sort of the idea. And so what does this do? Take a sequence, omega, and an integer n, and then associate to this specific function. Okay? So let's perhaps do an example. Let me not specify this iterated function system, but let's say that I have two contractions, and let's say that my omega is going to be a point in the sequence space with values 1 and 2. Let's say it is 1, 2, 1, 2, 2, 2, 1, 2, and so on. Okay? So this is, we call the ticker tape notation. This is just one point in the sequence space. So what is phi of omega comma 0, first of all? This is sort of like a technical definition in a sense. So here, this should be lowercase n. So what does it mean to take compositions from 0 to -1? It just means there is nothing there. So you just need to take this as the identity transformation. Identity transformation is certainly in the monoid generated by W. What is 1? Well, according to this formula, so lowercase n equals 1, which means that this is nothing but W sub omega 0. What is omega 0? Omega 0 is the 0th entry of the sequence omega. In this case, it is 1. Okay? So let's look at omega, comma 2. Again, by the same reasoning, now this is W sub omega 0 composed with W sub omega 1. Again, I look back into my sequence. So this is 1, this is 2. Does this make sense? So in my iterated function system, maybe let's complete this to an example. So for instance, the standard example, of course, is the Cantor set, or the iterated function system that generates the Cantor set, or one of them. Let's say this is like this. Okay. The moment you fix a sequence, you determine completely in which order you're going to apply these transformations. It says, oh, first apply this, then this, then this, then this 3 times, then this, then this, okay, according to this omega. If I had a different omega, the sequence would be different, and ultimately where I would end up at would also be different, okay? So in a sense, so in the Hutchinson operator perspective, what we did was we started with, let's say, a subset, and then we applied every single transformation here after one step. And then it sort of like grew and grew and grew. This is a different perspective where we choose one specific path, if you want. So this is like then So the Hutchinson operator does this. You start here, and then at the next step, you have all of these different possible futures, if you want. And then each of these futures bifurcate, or whatever, k-forcate, I guess, to more and more futures. So this is sort of like a parallel universes, perhaps, type of perspective, the Hutchinson operator, whereas the cocycle perspective is more like, oh, I'm choosing one specific branch, and I'm sort of following it to the end. Okay, that's sort of like the difference in the perspectives. Any questions about this? Yes?
I think mine's more of a prerequisite question, but
yes.
It's just confused me why, I think, so in the case of like the Cantor set or other invertible
yes.
Contractions, it doesn't matter if you order the WIs. Like, it feels weird to me that the outermost function is W sub omega c.
Yeah.
And the innermost is
Yeah, I was confused by that too, but this is the one that works somehow.
Okay.
Yeah.
All right.
Yeah. Yeah. Yeah, it is kind of confusing. So I didn't mention any of this, but there's all this business about left group actions or monoid actions, right monoid actions, and then left cocycles, and then right cocycles, and so on, and then you sort of like you confuse your left from your right, and somehow in different situations, different sort of like directions work. Let's just leave it at that. Yeah.
So this sort of perspective, when you're assuming, let me rephrase that a little bit here.
Yes.
For each indice here of omega sub 0 or omega sub 1,
yes.
you are assigning sort of one of the B-IFSs to that, and then giving that as a way to keep stacking them on?
Yeah.
Okay.
Yeah. Yeah. So I have here n different functions, and the entries of the sequence that I choose tells me in which order I should apply them.
Okay.
This is just, in a sense, a way to repackage everything. Any other questions? Now, let me mention one thing. Certainly, if I were to fix a sequence and an integer, this certainly has an element in the monoid generated by W. Okay? In particular, some of you have done this in previous reports. This is a composition of contractions. In particular, this itself is a contraction. On X, that means for any omega and n, there's a unique point that is fixed. Okay, I'm just gonna write it here. Remark. For any omega in shift space, and of course I need to take n to be at least 1. If it's 0, it's identity. Every point is fixed. Okay. There's a unique point x star that depends on omega and n in X such that the set of fixed points of this function is x star of omega n. This is immediately from the Banach contraction principle. Okay, so I have many sort of specific points that are fixed under certain contractions at this stage. Okay, so now the theorem. This is going to be a long-winded theorem to state and to prove to some extent, but it's not very sophisticated. So let's call this Hutchinson coding theorem. By the way, on the resources, I've put the original paper by Hutchinson. I think it's called Fractals and Self-Similarity or something like that. These are theorems. You know, the existence of the attractor too was a theorem in that paper. We're just basically following that paper, and so does Barnsley. Hutchinson does some more advanced stuff in there, using geometric measure theory and stuff like that, which we're not going to get into, but that's sort of the paper that we're looking into. And if you want to learn more about it, I would recommend having a look at that paper. On Math SciNet, this, you know, let's say, database for math papers, it has almost 1,700 references, which is quite a lot. So his second paper, the second most popular paper, has like 111 references. So there's a big drop off. So somehow this paper, a lot of people really liked it. Okay, so, oh, sorry. Before this, we need to, let's verify that this does have the cocycle property. So I want something like this. I want to have the sum of two integers here, and I want to be able to split that sum. Okay. So now this is, by definition, omega n minus 1, omega n, omega w sub omega sub m plus n minus 1. I just wrote this definition for with n here replaced by n plus m. The point here is that you see this first part is phi of omega comma n. But I want to identify this thing in terms of phi as well. So I have here, so let's think about this. I have here finitely many symbols, omega n to omega m plus n minus 1. In order to be able to write this piece in terms of phi, I need to be able to write it in such a way that this becomes omega 0 of some sequence. Well, the nth term of the sequence omega is the 0th term of shift applied to it n times. Okay, so right, that's what shift does. Moves it to the left, moves it to the left. So the nth term really is the 0th term of the nth shift of omega. And likewise, omega n plus 1 is the first term of the nth shift of omega. And finally, I have n plus m minus 1 is sigma to the n applied to omega at spot m minus 1. That is to say, this piece is nothing but sigma to the n of omega comma m. And ultimately, this is the reason why the ordering is this way. I want this property ultimately. Any questions about this? This is like a silly, like algebraic sort of manipulation, but it turns out to be very important. So, because phi happens to satisfy this property, so the sum of, so the value at the sum can be split this way. That's the definition for phi to be a cocycle. Okay, so now I can state the Hutchinson theorem. Okay, let's write it like this. 1. for any base point x or initial condition x in x, and for any sequence, if I were to feed x to this function, recall this is a function, it's a bunch of contractions after all. If I were to feed x to this function and take the limit as n goes to infinity for fixed omega, that limit exists. That I'm going to denote by capital phi of omega comma x. N exists. So this is going to be almost our coding map, except that we don't want this x here. We want it to depend on omega only. But we're lucky because it turns out that this limit doesn't depend on the initial condition. Just like in the Banach contraction principle, the limit doesn't depend on the initial condition also. So let's write it like this. For any x and y in x, and for any omega, phi of omega comma x equals phi of omega comma y. So I'm fixing the sequence, I'm changing the base points or initial conditions. That gives me the same limit. In which case, I might as well just drop this from the notation and just write it as capital phi of omega. Okay, so the limit doesn't depend on the initial condition. 3. Okay, the order in which I wrote these in the notes is very different, so I'm trying to rearrange them so that it makes more sense. 3. I want to say something about how this limit interacts with the cocycle, this lowercase p, and that's what it does. This is what it does. For any omega and for any n, phi of omega equals lowercase phi of omega comma n composed with uppercase phi composed with sigma n of omega. Okay. Then 2. So now it's 4. The limit in item 1, if I were to fix any compact subset of x, is uniform on that compact subset. For any a in h of x, the hyperspace, the limit in 1 is uniform over a. I'm going to mention what that means more specifically when we're trying to prove it. In 1 is uniform in a. Okay, next. So 5, okay. There are going to be 8 items. The image, so you see, this function now, at this stage, is from the shift space to x. But in fact, that's the context of item 5, or the content of item 5. The image is precisely the attractor. Okay. Then this. Okay. Now let's use this. So phi goes from the shift space to this, and it's onto. That's the content of 5. In fact, this phi function is Hölder continuous. 6, 7. For any omega sequence, I can identify phi of omega as a certain intersection. So this is a singleton that consists only of phi of omega, which is a point in X. So I'm saying that set is equal to the intersection of all the images of the attractor under these functions in the cocycle. And then finally, the attractor A sub W can be written in terms of these fixed points. Namely, A sub W is the union over all sequences and all positive integers of the fixed points of phi of omega comma n closure. It's a long-winded statement, but as we're sort of proving items, it's going to make more sense. I might leave this last one as an exercise and only give sort of some heuristics as to why it should be true. This is a very nice exercise. Barnsley also proves it in the book. But let me also mention here that in Barnsley, any such point is called a periodic point for the iterated function system. It's not standard terminology, so I'm not using that. Okay, and we're going to use this cocycle property to prove a lot of these things. So let's start with 1. And in fact, I'm going to start with a more general estimate. Proof. Let me take a compact subset first and take 2 points in it, x and y. Take a sequence and take 2 integers. Let A be a compact subset, x and y in A, n an integer. Let's write it like this. N and p integers. I want to bound the following. D of phi, and a sequence. I want to bound this. So I have 2 initial conditions, okay? 1 sequence, and to x, I'm applying this cocycle up to time n. I'm applying, on the other hand, the cocycle to the other initial condition more, in a sense. So I want to bound this. The point here is that, you see, here I can apply the cocycle property. So this is d of phi of omega comma n of x comma. So how do I open this? Recall that the cocycle property says this. This is the cocycle property. So I can replace this by this expression. The point of doing this is that now I have a factor on the outside like this. But then because I have another factor here, and because I know that it's a contraction, I can take that out. That's the point. Okay. Now this is the composition of the first, let's say, it's the composition of the contractions that correspond to the first n terms of omega. So I can bound this like this. I from 0 to n minus 1 Lipschitz of W sub omega I. Times E of x, comma, this. Okay.
Is the box intersection nested?
It's a product.
Oh, okay.
Yeah, it's a pi, capital pi. I'm taking the products of, or you can imagine it like this too. So recall that this function that I'm going to take out from both of these is this. Okay. So that means that I have n contractions in the first spot for the metric and in the second spot. So what I can do is I can take each of these out of the metric and have a factor like this. That's the point. Of course, the point here is that each of these is bounded by L, the max of these Lipschitz constants, which means that this product is bounded by L to the n because I'm multiplying it by n times. Any questions so far? Nothing sophisticated going on, but when you're first sort of dealing with cocycles for the first time, it's kind of bizarre to keep track of the manipulations. Okay, I'm gonna have to delete some of these. So this is good. But I want to bound it by something that doesn't depend on, well, it's going to depend on n, but I don't want it to depend on x. I don't want it to depend on y. I don't definitely want it to be dependent on p. So somehow I need to do something about this. Here's the trick. Let me just write it here. We're going to use Hutchinson operator with condensation. Use this set that you chose in the beginning as a condensation set and add it to the Hutchinson operator. So our notation for that was h of w comma a acting on the hyperspace. I had left it as an exercise to verify that this too is a contraction, which means that it has a unique fixed point. Okay, by the Banach contraction principle, there's a unique, let's call it a tilde in h of x, such that a tilde is the unique fixed point of this Hutchinson operator with condensation. Okay, now what is this Hutchinson operator with condensation applied to a tilde? So I can open it up. What it is that you're going to take every single contraction in W, apply them to A tilde, take the union, and then take the union of that end result with A as well. So ultimately this becomes A union Hutchinson of W applied to A, and then Hutchinson squared, so applied 2 times to A, and so on. In fact, you need to take the closure here, but that's not that important. What is important here is that because X and Y are in A, and because this is in so this is in A, and this is in Hutchinson applied, Hutchinson to the P applied to A. So I'm taking time P, basically. Which means that because Y is in A, this is also in Hutchinson to the P applied to A. But in any event, both of these are subsets of A tilde, which means that this is in A tilde, and so is this. Okay? Which means that this metric, this distance between these 2 points, is bounded by the diameter of A tilde, which is a finite number because A tilde is compact. In particular, it is bounded. Okay. So ultimately, I was able to bound the distance between this and that point by something that depends on n, that decays exponentially with n, that doesn't depend on anything else. Yes?
The argument made sense to me. I'm just confused about the A tilde equals.
Yes.
Why are the arguments of the Hutchinson operators A's and not A tildes? They're on the line above.
Oh yeah, I mean, okay. So, okay, let's say a couple more words about this. I'm just gonna here. All right, more generally. So, what is the Hutchinson operator with condensation A applied to some set B? Well, this is nothing but A union from I from 1 to n, W sub I applied to B. Okay, that's the definition. So this is a standard Hutchinson operator. When you have condensation, you take the union with this other set as well. Okay.
So then isn't B in our case A tilde? So on the
No, this is just some arbitrary set. I'm saying how it operates. But now we need to look at this equation. Okay? Now A tilde equals, so I'm just going to open up this left-hand side, A union Hutchinson operator applied to A tilde, you're right there. So from I from 1 to n, W sub I, A tilde. Okay, but then I can keep applying this property. A tilde itself is this. So replace this by this expression. So A union I from 1 to n, Wi, and inside A tilde, I'm going to see this, which is A union, let's call it J, 1 to n, Wj, A tilde. You keep pushing it like this. That's why you have an infinite expression. And this is like a nice trick. And that's why ultimately you need to take the closure. Yeah. Any other questions about this? Did I lose you? Okay.
I think I need a little bit more emphasis on how you're taking A tilde to be this union of unions, and how that gets you closer to finding this L to the n diameter of A tilde.
Are you happy with this part?
Yeah, that makes sense.
Okay, so by continuing this operation, basically, I'm going to have a bunch of A's and these attractors applied to it. So at the next step, I have A union. So let me just abbreviate this union by Hutchinson applied to A, and then I distribute. Okay, so this piece, so you take this, apply it to this, and then you apply it to there. Okay, A, and then now you have two unions, and inside it you have an A tilde. Again, you replace it to get another copy of A. You keep going like this. Again, let's not worry about the closure. You need to take the closure ultimately. So maybe the question is why this point is here?
Sort of that as well, yeah.
Okay. Y is in A. I started like that.
Yeah.
No matter what the sequence here is, if this entry P equals 1, that means that I'm going to take Y and I'm going to apply one of the contractions, just once. So let's write it like this. Phi of eta, comma 1 applied to Y means whatever this sequence eta is, I'm just applying one contraction once, which means that this has to be in the Hutchinson operator applied to A once.
That makes sense.
Because this set contains all possible images. Well, if this number were 2, that means I'm applying 2 contractions. Ultimately, that's going to land somewhere in the Hutchinson operator applied twice to A, which means that, you know, by induction and so on, this means that this has to be in Hutchinson operator applied P times to A. Is that okay?
Yeah.
Okay. A is a subset of A tilde, and so is any iterate of it under Hutchinson, which means that this is a subset of A tilde, and so is this.
Okay, that makes sense, yeah.
Okay, which means that this point and this point are both in A tilde, which means that they're bounded by the maximum distance between any 2 points in A tilde. That's the definition of the diameter of a set.
And then because of the compactness,
Yes.
we can say it's less than infinity?
Well, I mean, compact sets are bounded.
Okay,
Yes.
that makes sense then.
Any other questions? Okay, so we have this estimate. That's good. Let me delete most of it. So ultimately we have this. Let's just say C times L to the N, C is some number. In particular, if X is equal to Y, that means that I have a Cauchy sequence. So choosing X sub n defined by phi of omega comma n applied to X, right? So this is the nth term of the sequence. This is the n plus pth term of the sequence. Is bounded by something that decays in n that doesn't depend on p. That means that it's Cauchy. X is complete by the definition of the B-IFS. So you need to start with a complete metric space. It has a limit. Is complete. There's a unique point. At this stage, that's going to depend certainly on omega and on the initial condition. So this sequence is Cauchy by the completeness of X it has to converge somewhere. That limit at this stage might depend on omega and x. It's always going to depend on omega, but we're going to see in the next item that it doesn't depend on x. Any questions about this? Yes?
Can I think of little phi of omega n as like an approximate decoding? Or like what, I guess?
Yeah, you can think of it as like a finite resolution
Okay.
coding, yeah. Yeah. Okay, so that is done. Item 2. So let's write it here. 1 OK. For 2, again, I'm going to use the same estimate here. This estimate is the important estimate that we keep using. Okay. So for 2, what I can do is I can look at the distance between this and phi of omega comma y. So I'm putting in the wrong initial condition and see if I can bound it. This. Now I want to bound this expression. If I can bound this as n goes to infinity by something that decays, that means that this term converges to this. But limits in metric spaces are unique. So a sequence, if it converges, cannot converge to multiple points. This is another way of saying that the space is Hausdorff. Okay, so what I can do is this. So I'm going to inject here phi of omega comma n applied to the point x. And then, of course, I have this term. Okay. Now, this is bounded because of this. Here, I could take p to be 0, for instance. This is bounded up by something that decays exponentially fast. And this, too, I can... let me just write it plus epsilon. And then that does it, right? Because if I were to fix an epsilon, because in part 1, we showed that this sequence converges to this, there is some lowercase n such that this distance is less than epsilon. And likewise, there is perhaps some other n that is perhaps larger, such that this is less than epsilon as well. So that I can bound this expression by something that is less than 2 epsilon for any epsilon. Which means that taking epsilon to 0 by the n epsilon of room principle, this distance has to be 0. There's no other way for this metric to be, this distance to be less than any positive number. Questions? So this limit doesn't depend on the initial condition, so I can just write it as phi of omega. Okay, let's take a 5-minute break. When we get back, we're going to continue with item 3. Okay, welcome back. Let's continue. So we showed that the limit exists. So you fix a point here, x, for instance. You fix a sequence. You let n go to infinity. That converges to some point, and it is very nice in the sense that it satisfies this estimate. I wrote it here so I can actually get more space here. Item 3. I want to say something about how uppercase v interacts with lowercase v. Okay. Again, I'm going to use the cocycle property. So what is this? Limit as n goes to infinity of lowercase phi applied to omega comma n of x. Some x. I don't really care at this point because in item 2 we show that that limit doesn't depend on x. Now what I can do is, maybe I should use here m. Well, I can switch to a certain subsequence of this, which is given by n plus m, for m fixed. It's a subsequence. I just discarded finitely many terms, so the limit is going to stay the same. And then to this, I can apply the cocycle property. Limit as m goes to infinity of phi of omega comma. So the first guy is n, composed with phi of sigma to the n of omega comma m. I just applied the cocycle property. Now, this is fixed. It's a fixed function, okay? And it's fixed here. In particular, this is a contraction, which means that it's continuous, which means that I can take this outside the limits. But then this is nothing but phi of sigma to the n applied to omega. Which is what we wanted. It's not that complicated here. So 3. Okay. Yes.
Can you explain a little bit what this composition of functions is doing? Like, I guess it just I can verify that it's true, but I have no idea what it means.
So for instance, in the Cantor example, you have two contractions. And once you fix a sequence here, you know in which order you should be applying those contractions. So you fix a point, let's say. It's not going to matter based on item 2, but let's say for simplicity, you fix a point and you start applying these functions. And based on that, it sort of like goes somewhere. So it's almost like, maybe you should think of it like this. If you had only one symbol, if capital N was 1, so that you have one contraction, you're basically applying the same contraction over and over again. Here you have multiple contractions, but again, the limit exists. Okay? So it's like a Banach contraction principle, but applied to a bunch of contractions, not instead of just one function. Does this sort of make sense?
Well, yeah, I understand little phi, but it's just like I guess the bottom line, the thing that we're proving big phi is equal to, it doesn't make sense what each piece of the composition is doing. So like I guess an alternate. Yeah, does that make sense?
Okay. So let's parse the expression here.
Particularly it feels weird to have little phi left of big phi. That's what
Okay. Omega is a sequence, which is a point. I can apply shift to it n times. That's another point in the sequence space. Now taking this limit, this is the limit of a sequence of points in x, which means that this is a point in x. But then this is the composition of finitely many contractions of x. In particular, this is a function from x to x, which means that whatever this is. If you want, I can write it like this. Does this make sense? Okay. Yeah. Okay. Item 4. So far, when we were looking at the limit and so on, I didn't really care that much about the dependency of, let's say, the lowercase n, that would make the distances less than epsilon, let's say, to the base point x. The limits might be the same, but that doesn't make it so that the convergence is uniform. So let me write more explicitly what this means. So for item 4, what I want is this. I fix an A, okay? And let's fix a sequence. Then I want this. For any epsilon, there is a capital N, such that after capital N, for any x in A, the distance between lowercase phi applied to omega comma n, then applied to x, and the limit is bounded by epsilon. So far what we were doing was basically the same statement, except that this, for any x in A part, was outside. It was over here. Now I'm putting it over here. Okay? So that if this x were outside, this n could depend on epsilon nx. If this x is inside, this n, the time that makes this metric, this distance, less than epsilon, cannot depend on x. Okay. Okay. So again, let me just try to bound this. Okay. How can I bound this? Well, we just proved this property that allows me to create a factor like this on the outside. So let me just replace this by this. Okay, so now this guy I see in both of the arguments, which means I can take it out, and I get a factor of L to the n, which decays. And then this is d of x comma phi of sigma n omega. Okay, now this is, again, this expression is bounded by the diameter of A tilde. So I had fixed A. I apply this Hutchinson with condensation operator and so on. I get a fixed point. This A tilde is that A tilde. So the moment I fixed an A, I knew what this bound was. But you see, I was able to bound this by something that doesn't depend on x. For any x in capital A, this bound is going to work. Which means that for any epsilon, there's a capital N such that this is less than epsilon for any lowercase n after uppercase n, such that for any x in A, this is bounded by this, which itself is bounded by epsilon, which means that this limit is uniform in A. By the way, if it's not clear, I think it's a very good exercise to verify that this thing is in the attractor A sub w. And furthermore, this is a subset of A tilde. Okay. Maybe it's not as straightforward, but it's a very nice exercise to see this. Questions? Okay, so that's 4. 5. Now, this exercise really says that the image of phi is a subset of A tilde. Now we want it the other way around though. I want to say, if I were to take any point in the attractor of the iterated function system, there is a sequence that phi takes to that point that I chose. Take a point in the attractor. What I want is a sequence. I want to be able to build a sequence omega I'm not claiming that this omega is going to be unique, okay? I just want one. Omega such that P of omega equals A. Any guesses as to how I can do this? We need to use the fact that this A is in the attractor. The attractor is defined by a certain equation, okay? So we need to again try use that equation. It's a set equation, but it's an equation nonetheless. So A is in A sub W. But A sub W, by virtue of it being the attractor for the iterated function system W, I can write it like this. Like this. Right, so because A sub W is supposed to be the unique fixed point of the Hutchinson operator. If this is the case, that means that there is some point in the attractor and some index such that A equals W sub I applied to that point. So there is an A1 in the attractor, and there is an index, let's call it, or maybe I should say A sub 0, and there is omega 0, some number between 1 and n, such that A equals W sub omega 0 applied to A sub 0. It has to come from somewhere. So this point that I fixed comes from some other point in the attractor when I apply some contraction to it. Maybe there are multiple such omegas, but I'm just taking one number. But then, by the same reasoning, I can write it like this. I can take this A sub w inside and replace A sub w here by another union. Okay, so I have two unions now, which means that there is some W1 and there is some A1 and A sub W. There is some W1 between 1 and n, such that A equals W sub omega 0 composed with W sub omega 1 applied to A1. Going this way, I have a sequence of points in A sub W and a sequence of symbols from 1 to n such that there's an omega in shift space, there's an A sub bullet sequence in A sub W, such that for any n, A equals phi of omega comma n applied to A sub n. So this is phi of omega comma 0, sorry, phi of omega comma 1, this is phi of omega comma 2, and so on. And just keep applying this. At each step, I'm just replacing this A sub w inside the Hutchinson operator by another copy of it to get more and more unions. The claim is that phi of omega, the sequence that I created, equals A. Okay. Any questions about this argument here? Later on, maybe if things are getting too abstract, it might be good to go through sort of like the steps of the proof using the specific example of the Cantor set, or rather the iterative function system that generates a Cantor set. So we have this, and the claim is that A equals phi of omega.
That's big phi.
Yes, yes, big phi, yes. So this is what we have. Where omega is this. Well, I'm just going to try to bound the distance between these two things. Okay, A equals that thing. And again, let me just not write it explicitly. Again, I can replace phi of omega by this expression and then pull out this factor to get a factor of L to the n. In which case I have, and then over here I have this omega. Okay, so this is in the attractor. This is in this also is in the attractor, which means that this is bounded by the diameter. Again, the attractor is compact, which means that this is a finite number. So you see, this is bounded by something that decays in n. But on the left-hand side, I don't see any n whatsoever, which means that if I were to take n to 0, that means that these 2 points have to be the same. So, given any point in the attractor, I was able to come up with a sequence that phi takes to A. That is to say, phi is onto, so from shift space to the attractor. Questions? We have a couple minutes. Let me see. This takes some time, but I think I'm going to finish early. Maybe we can discuss some questions. This is, so we're going to do this, and this next time. I might give this as an exercise, but I want to say some stuff about this. It's not that complicated, but it's a very nice argument, and I would highly recommend that you sort of try to do this by yourselves. But it's a very nice exercise. So any questions about stuff that we did so far? How many of you did I lose? Kind of, sort of, okay. In the 50th time you're going to hear the word cocycle, you're not going to flinch. Okay? It's all about cocycles. Dynamics is 95% about cocycles. Even though people may not use the word, underneath sort of whatever they're trying to do, they're really trying to understand a certain cocycle and how it operates. In this case, as you see, this uppercase phi is a limit of the cocycle, and the dynamics is really encoded in the cocycle itself. It's not really in the phi. Yeah, no, it's so there are these things called there's something called cohomology in math in general, which are basically gadgets that tell you when two things are homologous or cohomologous, are sort of similar to each other. And so this is sort of like the dynamical version. In a much more sort of in nicer settings, you have like this whole like algebraic theory. In dynamics, cocycles are, or the theory of cocycles or cohomology is a lot more volatile. Like you have to sort of do a bunch of like limits and so on to make things work. But so ultimately a cocycle, or this theory of cohomology is ultimately a generalization of the fundamental theorem of calculus. So you want to say something like, let me just write it here. So for a single variable, what is it? So a b f prime of t dt equals f of b minus f of a. Right, so, and in multivariable you sort of like have more general, more like higher dimensional versions of this, Stokes theorem, divergence theorem, all that stuff. But it's all about this idea. You have something here. Either you differentiate a function, or you take the integral of the derivative of a function on the whole thing, on the bulk, or you can integrate this, the function itself, on the boundary. Now, for instance, this interval here is called a cycle in a different terminology, and the boundary of this is the point A and point B. So this is called the one form and so on. So this, in a sense, is a one cocycle, if you want, in a different sort of like framework. But it's all about fundamental theorem of calculus. I put under the resources a paper which is sort of like hard to read, but it's a paper by Manin. He's talking about the notions of dimension in different contexts, and there he's talking a little bit about this. Manin, yeah. He passed away last year. He's a very good mathematician. Okay. So yeah, I mean, for now, in dynamics at the very least, there are certain formal analogies of cocycles in dynamics and cocycles in other areas, and people who know a lot better than me at one point decided to call these cocycles, and now everyone calls it cocycles. Yeah. Okay. Thank you. We're going to continue on Thursday with the proof of these. Okay, let's start. Good afternoon. So today I'd like to finish the proof of this Hutchinson coiling theorem. I want to do some more stuff, namely this lifting construction that allows you to start with any iterated function system in the sense of Barnsley whatsoever, and then build sort of a more complicated iterated function system that happens to be totally disconnected. There's also something called shadowing, and this notion of a chaotic dynamical system that is due to Devaney that I wanted to discuss. Probably we're not going to be able to cover it today, but on Monday we will discuss some of these more dynamical ideas, mixing transitivity, sensitive dependence on initial conditions, and all that stuff. But before we get to this proof and everything else, I thought it would be a good idea to have a look at this final report and presentation specification. I hope you had a chance to have a look at it. So maybe I should ask if there are any questions about it. Yeah.
So one thing that I was very curious about is in the weeks leading up to like writing this first
Yes.
draft, or I mean even continuing after the first draft,
Yes.
would it be fine if our reports are more structured around this working towards this final report? Would you rather than
I would say so, yeah. I mean, I would even say, you know, like going forward, maybe starting from next weekend even, it would be good to sort of restructure your reports so that their focus is sort of like building up to the final project.
That's what I was thinking about. I was curious if you wanted to be more
Yeah.
disconnected.
Yeah, I mean, you can sort of like just keep studying different things as well, of course, but I think, I mean, you only have so much time and you can only understand so much stuff, right? So instead of sort of trying to understand or, you know, trying to solve this exercise or that exercise, I think at this stage it would be good to sort of switch over to something more sort of grand in scope and just like start sort of working toward it. That's what I would think, yeah. Okay. Okay, so yeah, it's the same stuff as the weekly reports, of course. I'm expecting you to all to work on different things. So the deadlines are so that, you know, I'm sort of asking you to start working quite early on, actually. But I'm asking first, for instance, at the end of week 9, which is in 2 weeks, I think. So this is week 8, so week 9 is next week. To declare the topic and primary sources. So it's like a white paper, if you want. It doesn't need to be conclusive, of course. It might be that, you know, I might ask you to sort of make some adjustments or something like that. But at the very least, you should have some idea as to what you want to work on. And then at the end of week 12, I want the first draft for the written final report. Again, it doesn't need to be sort of almost done, but obviously, it's like probably the closer, the more details there are in the draft, the more feedback, the more constructive feedback I'll be able to give. Like if you don't write anything in the draft, it's like I won't be able to sort of point out anything. And then 1 week after, week 13, I'm asking for the draft for the presentation. And then at the end of week 15, we have the final report, final submission. Okay. Let me think. Yeah, examples of acceptable content. I sort of listed a bunch of different things, so you can focus on certain topics in the textbook, in Barnsley's book, or in Falconer. I've been looking at some theorems there, and like there are certain rather advanced theorems, but I think it would be very good to sort of study one of these theorems and like give the proof and perhaps applications. So one of the things that I looked at the other day was this idea of the sundial, or digital sundial, I should say. So the idea there, and this is a theorem in Falconer's book, and then someone else sort of realized that you can't actually use this idea and actually produce an object that does this sundial thing, but at the very least you can sort of adjust it a little bit. So the idea is that, so this is not the proof, digital sundial. So the idea is this. You have, let's say, you have the ground, something like this, and then you want to here put some object, let's say it's like a box. It's going to be more complicated than that. But the point of a sundial is that when the sun is moving from here to there, this object is casting a certain shadow. And this shadow keeps moving, of course, as time moves on. And basically, based on the position or perhaps the shape of the shadow, you can say what time it is. That's the idea of a sundial. The point of it being digital is that here you want to have sort of one machine, one object, such that here in the shadows you see the appropriate time. That is to say, let's say if the sun is here at 7 a.m., you want the shadow to be of the shape, 0, 7, 0, 0. And then when you're over here, you want it to be 14 or something like that. Of course, the point here is that this set is going to be very complicated in order to achieve this. So imagine sort of like a shape such that no matter, so depending on from which side you're casting a light, you're getting a different shadow. These type of objects are kind of interesting. And using fractal geometry, you can actually prove the existence of such a thing, at least in principle. And so the way you do this, and so this is a theorem that Falconer mentions in the book, but you can do this in higher dimensions as well. So this is a two-dimensional version. Instead of sort of having the sun move around, you move the plane, or in this case, it's going to be the line that is going to be that the shadows are going to be projected onto. So you want to have here a set. It's going to be a bizarre fractal set. And let's say that this is the origin. And let's say that you have this line, and this is the x-axis. Let's call the line that makes an angle of theta from the x-axis L sub theta. So this corresponds to having the sun over here. And as you're moving, as you're increasing theta from 0 to pi, I guess, you're sort of moving the sun in a sense. And of course, what you can do, this is sort of like a linear algebra thing perhaps, that whenever you have something like this, whenever you have a line, we have orthogonal projections. Okay, so you take the set, you project orthogonally, and then you have some other set here. Now, this is the statement, roughly speaking. So, for any angle, choose a subset, let's call it S for shadow, S sub theta, in this line. Okay, you choose it for any angle. Then there's a set that is fractal. There's a fractal set such that for any theta, the orthogonal projection of the set that you constructed to the corresponding line with the corresponding angle is the set that you chose. This is not exactly true. There are certain technicalities, not for all theta, but for almost all theta and so on. But this is sort of like the main idea, which means that given any set of shadows that is prescribed, you can come up with a set that actuates that set of shadows, which is, I think, quite interesting. So this could be sort of like a project, the proof of this and so on. I put a couple papers about this. There's a US patent of some digital sundial that at least mentions this idea and so on. So you can approach this from a pure point of view or applied point of view, or maybe both. And there are many other ideas that we can come up with. Is this sort of like making sense a little bit at the very least? Yeah. Okay. Okay. First draft, final submission. Style formatting is the same. I want it to be on LaTeX. Presentation. So I'm going to ask you to submit a draft for your presentation. If your presentation, so the presentation is going to be in week 15. It's going to be around 10 minutes, and I'm sort of currently organizing in which order the presentations are going to be. But ultimately, I'm letting you choose between sort of like a PowerPoint, or if you're using LaTeX, Beamer presentation, or a chalk talk is what people would say. You can do either, but in any event, I want some sort of draft by the deadline, so that you're not cramming your presentations or reports and all that stuff. Apart from that, I think it's not that different from the weekly reports as far as I'm concerned. Okay. Good. So now let's get back to the Hutchinson theorem. Let me remind you, we have the setup. I have a B-IFS, which by definition means that I have X, which is a complete metric space, and I have finitely many, 1 to n, contractions. Regarding notation, perhaps I should mention something. So the name of the IFS is uppercase curly W, okay? So the IFS itself. So by definition, an IFS is a collection of functions. So curly uppercase W. Okay. One function in your IFS, so an element of the IFS, W, lowercase w. Omega, which is this curly type of W, at least that's how we write it, is an element in sequence space or shift space. So lowercase omega. Or maybe eta, if I'm using sort of a different sequence or a different point in sequence space. So I switch to Greek if you want, whenever I switch the shift spaces. And then omega sub k would be an index or an entry in this sequence, but that entry is going to be some number between 1 and n. So omega k, let's say, some number between 1 and n. Maybe I should have used sort of different letters, but this is like how we started writing iterated function systems, or how I started writing iterated function systems. I think this is also what Barnes uses, but then Barnes uses sigma for elements in shift space, but I use sigma for the shift dynamics, so I can use sigma for the for a point in the sequence space and so on. So just so that I don't overload the symbols. And of course, you know, whenever you're reading something, it's important to permute every single symbol to some other thing so that you confuse everyone else. But anyway, okay, so we have an iterated function system. L is going to be the Lipschitz constant, or the maximum of the Lipschitz constant. By definition, it's some number less than 1, between 0 and 1. A sub W is the unique attractor for the iterated function system. Sigma, uppercase sigma plus is the shift space with symbols 1 to n. You see, I have one symbol for one function. Recall that we had this cocycle, lowercase phi, going from shift space times integers to the monoid generated by W, which is basically this. You take a sequence, you take the first n terms of it. Those n terms correspond to n contractions in your iterated function system. You compose them in this order, which in particular gives you another contraction, of course. And then we were discussing this Hutchinson coding mapping, uppercase phi, going from shift space to the attractor, which is defined like this. You take a sequence, you take any initial condition, lowercase x, and then you apply your cocycle to this initial condition, and then you take time n to infinity. We showed last time, as part of this Hutchinson coding theorem, that this limit exists. It doesn't depend on the initial condition x. This convergence is uniform when you're restricting your x to be on a compact set and so on. A bunch of different things. Any questions about this so far? So we had 3 more items remaining. So let's first look at item 6, that this phi function from the shift space to the attractor is Hölder. In particular, it is continuous, of course, but it is more. When we start talking about dimension, at least Hausdorff dimension, continuous functions or merely continuous functions or even merely uniformly continuous functions don't necessarily preserve dimensions. And Hölder functions too don't preserve, but at the very least you have some estimates. That's going to be useful later. Okay, so I need to show that this is Hölder. Now so far in the proof, if you recall, I actually never changed the sequence that I was using. It was always 1 omega. Now I need to have 2 sequences, 2 points in shift space. So I want something like this. I'm going to take 2 points in sequence space, omega and eta, arbitrary. I'm going to apply my coding map to them so that I have now 2 points in x or the attractor so that I can look at the distance between them. I want to bound this distance by an expression of the form a constant times distance between omega and eta to some power. Distance relative to what? One of these d theta metrics. I want some alpha like that. So here recall that theta was some number greater than 1. Okay. So let's recall this d theta metric. Maybe I should write it over there.
Is it the alpha that's greater than 1 or theta?
Theta, yeah. Alpha can be any number.
Alpha be any number?
It's a positive number. Well, if you looked at the notes, in the notes I might have used theta for the Hölder exponent, but I'm changing it now. So, I mean, even in the notes, I did use alpha and theta and other things for the Hölder exponent also. Okay, so let's recall this d theta metric. Theta is fixed, okay? What was this? This was an infinite series. Let's use this definition. Delta of 2 things here was the discrete metric. So it's going to be 1 if they are the same entry, or 0 otherwise. So maybe I should write this out explicitly as well. Okay, so starting from 0, I have this plus 1 over theta, delta of omega 1, eta 1, plus 1 over theta squared, delta of omega 2, eta 2, and so on. So let me also remind you These were points in sequence space or shift space. Using ticker tapes, I could represent them like this. It takes a while to come to terms with even the shift space as a metric space. That is nice, I understand, but it's very useful. So what does this do, right? So theta is a number that is larger than 1, which means 1 over theta is less than 1. So this multiplier, if you want, the farther you go when comparing the entries, the less that sum end is emphasized, because this part is always decaying. And this number, this delta, is either 0 or 1. So it cannot be something crazy. And the farther you go when comparing the distance between two points in sequence space, the less you're going to emphasize it. Similar to how you would sort of look at the distance between two real numbers when you're just looking at their decimal expansion, if you want. Okay, so we had talked about this before, but if I were to choose two of these, well, there's a first entry somewhere that they're going to start disagreeing. Maybe it's at 0, so maybe omega 0 is different from eta 1, or maybe omega 0 is the same thing as eta 1, but omega 1 is different from eta 1, okay? And so the farther away the disagreement, the closer 2 points are in sequence space. So maybe I should write that. Recall. In shift space, the farther away, let's say, from the 0 entry, the disagreement is, farther, let's say the farther the disagreeing entries are, the closer the 2 points. Okay. And in any event, I can always find, given any 2 points in sequence space, I can find some, let's say, n integer such that this distance is bounded by 1 over theta to the n. It's less than that. And it is at least 1 over theta to the n plus 1. So this means that omega and eta agree when you just look at the first n entries of them, where n is less than capital N. Because if they didn't agree, I would have sort of like a term here that is greater than this. Okay, that's the idea. Yes?
And when you're saying don't agree, that just means 2 entries at a certain point are of different values, or?
Yeah.
Okay.
Yeah. Exactly. Okay. Okay. So let's do this then. Once I fix my omega and eta, I have an n like this. I'm fixing that n as well. And so now I'm going to use this property that we proved last time, which says something about how uppercase phi interacts with lowercase phi. Recall that we had this relation. So that means that you can generate one of these terms in the cocycle outside the uppercase phi, but the trade-off is that inside you're going to have to apply the shift the appropriate time. So we're going to use this. Okay. Yeah, I can do that, or I can do something else actually. Yeah, let me do something else actually. Okay. So, okay. So I want to control this metric, this distance over here. Instead of using this, I'm going to use something much more straightforward. So let me just erase this. Namely that the cocycle sort of converges. So these are the limits of cocycles. So if I were to inject here, oh, I guess I was going to use it after all. Oh, maybe not, actually. So this okay. That plus this term. So I applied the triangular inequality a couple times here, right? So I first put this in, and then I put this term in, and then I have like what, three things now. The point here is that uppercase n is fixed, but lowercase n is arbitrary. And I know that as I take n to infinity, this term applied to, let's say, some initial condition, it's not going to matter, of course. I know that as I take lowercase n to infinity, this term converges to this. After all, this is, by definition, the limit of the sequence as this goes to infinity. And likewise, this term, you see, is going to converge to this. So this distance, I can bound by epsilon if I choose lowercase n large enough. And likewise, this term too is less than epsilon if I were to choose lowercase n large enough. Okay. Now what to do with this? Well, I'm going to use this trick that I used last time, which is this. So recall last time we did this business. We had sort of like an initial condition, and then when we were comparing, for instance, 2 points or something, we chose those 2 points from the same compact set. Well, let me choose as my A the singleton, that is x, okay? Then applying this Hutchinson operator with condensation, which is a contraction, I have a unique fixed point, which is this A tilde. Okay, and on Tuesday too, one of the important ideas was that this term is going to be always a term, always a point in A tilde, and so is this. That is to say, this is bounded by diameter. Oh, but I want one thing. Ultimately, I want to be able to see this distance, so I need to take that out. Okay. So here I'm going to use the cocycle identity then. So let me do it here. So continuing from here, so I have 2 epsilons plus this term. Omega applied to x, comma, phi n plus n, comma, eta applied to x. Now using the cocycle identity, recall, maybe I should remind that as well, the cocycle identity said this. Well, PQ, and then zeta equals phi of p, hang on a minute, change the notation, sorry. The way we wrote this was the other way around. Zeta p plus q equals phi zeta p composed with phi sigma to the p applied to zeta, comma q. So maybe I should write that properly as well. I apologize, I'm not going to rewrite this part, but I sort of mixed up the arguments here. It should be the other way around, based on our notation. But in any event, applying this cocycle identity, we have this now. D of phi of, hang on a minute. Oh, okay, that's fine, that's fine. Good. Okay. Pose with phi sigma to the n omega comma lowercase n. Okay, this is a tricky proof. This is the first piece, and then the second piece is phi of lowercase eta comma n uppercase composed with lowercase phi sigma to the uppercase n applied to eta comma lowercase n applied to x. Okay, now I have here one contraction, I have here another contraction. If I could get rid of this term and this term, I'm basically done, okay? Any ideas as to what to do here?
We know the contraction, like upper bound for the contraction constant.
Well, that's true, but this is a different sequence than this. You can, but you don't need to. Okay, this is the tricky part. Okay, this is why this works. Okay. We said that I chose this capital N such that this happens. In order for this to happen, it must be the case that the first n terms of omega and eta are the same. Now, even though omega quite possibly is different, it's a different sequence than eta, I know that the first n terms coincide, which means that this contraction is actually the same contraction as that contraction. Okay? Which means that I can pull it out, and I would get a factor that decays. So I would have 2 epsilon plus L to the capital N, because I have n contractions, and then this distance. Let me not write that part. This is just it's just going to be bounded by the diameter of that A tilde set that I was mentioning. It's some number. Okay? So, that is to say, let me just write it like this. C times L to the N. C is this number. It's not that important, because in the Hölder inequality, or Hölder estimate too, this number that we don't, it's not, at least for this context, it's not that important what exactly that number is. What is important is this. We still have this. Somehow I need to get rid of this. But let's think about this uppercase. So the argument here was this. I chose omega and eta. By definition, they have to satisfy an inequality like this for some capital N. I choose an epsilon. Let epsilon be positive. Then, because of this identity, I know that there is some n, lowercase, such that this distance is less than epsilon, and so is this. But then I can apply this trick that omega and eta coincide up to the first n terms, which means that I can take this out, and then I have this expression. So ultimately, I was able to get something of the form, for any epsilon, this distance is bounded by 2 epsilon plus c times L to the capital N. Well, I can take epsilon to 0 to get rid of this piece. Okay. Or if you want, I can take infimum over epsilons. And then I have this. Okay?
Do we need the inequality to be strict since we gave up an epsilon?
No. So here, so the inequality is strict here. But when you take the infima, the boundary you have to include. Yeah. It's not that important, of course, but in any event. So we're almost there. Because note, L is some number less than 1. So if I can change the L over here to 1 over theta, I can sort of get rid of this, or put that there. And in fact, I can do this. We did this trick before. Let me not do that again explicitly. There is some C prime, let's say, such that this happens for some alpha. So here I changed the base of this logarithm, if you want. We had used this trick before too. So alpha is going to be dependent on these numbers, but at this stage it's not that important what exactly alpha is or how it depends on the other variables. Okay. So ultimately, I was able to show that it does satisfy a Hölder estimate for some alpha. Okay. I feel like I cheated here a little bit, but it is true. I can empathize with you. If I was listening to this argument and if I didn't know how to do this type of stuff, I'm not assuming that you don't know, but if I weren't very comfortable, let's say, I would feel cheated by what I did over here, but maybe we can discuss that later. But any questions apart from that? It's ultimately a technical trick. Okay, so that shows that this is a Hölder function. So we have that. How about 5, 6, 7? Now for 7, we need to understand this intersection on the right-hand side. Question? No?
Oh, no,
Okay.
sorry, I was kind of
Yeah. So we know that because this A sub W is the unique attractor, it's the fixed point of the Hutchinson operator, which means that I can write it like this. Let's write it like this. So I, W sub I, A of A sub W. In particular, recall that this just means I'm applying one contraction. It's a certain subset, right? Because this basically here it's actually nothing but this. W sub omega 0. Omega 0 is one number between 1 and n, which means it is one of these. So this term is one of these sets that I'm taking the union of. Okay. In particular, this part has to be inside. Okay. Well, I can keep applying the same idea. This is also, right? So because we used this idea before too. If A sub W equals the fixed point of the Hutchinson operator, it's also the fixed point of the Hutchinson operator applied twice. So I can replace this by a second intersection. Which means that not only this, but in fact, if I were to take any two contractions and apply, look at the image under them of A sub W, this is going to be a subset of this, which of course is a subset of this. What I'm trying to say here is that if you generalize this idea, as n goes from 0 to infinity, this really is a sequence of decreasing sets. So okay. Each of these sets is compact because A sub W is compact, and each of these functions are contractions. In particular, they are continuous, and continuous images of compact subsets are compact. So I have a decreasing nested, or you can say it that way as well. I have a nested sequence of compact non-empty subsets. Well, that intersection have to be a point. Maybe I should leave that as an exercise. Is a point. One way to show this is to realize that the diameter of these sets goes to 0. And in fact, that intersection is going to be the what was it? Pompeo-Hausdorff limit of the sequence of sets, if you want. And maybe I should leave that as an exercise also, that this point, this phi of omega, is going to be inside all of these. Exercise. This point is in the intersection of all of these sets, which means that this point is in the this intersection, but the intersection is at most one point, which means that it has to be that point. Okay. That's how you prove this. Questions about this? Okay. Let's have a look at the final item. Let's see what this says. The final item says the following. The unique attractor for the B-IFS W is the closure of all fixed points of all of these contractions. So I look at all sequences and all numbers starting from 1. Recall that this now is, it's a composition of contractions, which means that for any omega and n, phi of omega comma n, phi of omega comma n is a contraction. It's acting on a compact metric space, or a complete metric space if you want, which means that it has a unique fixed point, which means that this set of fixed points is actually 1 point. I'm taking I'm taking the union of countably many singleton sets. Okay, and then I take the closure of this. Now what does this mean? When you take the closure, or saying that this set is the closure of this other set, it really means that for any point in the attractor and for any epsilon, you are able to find some contraction like this, some element of the cocycle, whose unique fixed point is epsilon close to the point that you chose. So you can approximate arbitrarily well any point in the attractor using a fixed point of one of these contractions. Okay. I'm going to leave this as an exercise because it's a very nice exercise. Fundamentally, you want to use, one way to see this is to use the coding that you built at this point. So you want to take a point A in the attractor. You know that the Hutchinson coding map, uppercase phi, is onto, which means that there's at least one sequence omega that phi maps to this point that you chose. Now, how do you approximate that sequence in sequence space? Well, we need to think about that a little bit. But once you can approximate it in the sequence space, you can again apply the Hutchinson coding to get the point in the attractor. Okay. Okay, let's take a 5-minute break. When we get back, I want to say a couple more words about this item specifically and how one can use this. Because there's a bunch of pictures in the Barnsley book. He has like this attractor, when he has a fractal, and then he has a bunch of arrows and stuff like that. I want to sort of make sense of that a little bit, but ultimately this is now an exercise. Okay, let's take a 5-minute break. Okay, welcome back. Let's continue. So here I wrote this again. For any omega and n, phi of omega n is a contraction of X, the complete metric space. By Banach contraction principle, it is a unique fixed point. You have other things, estimates and blah, 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 but this is sufficient for now. So recall that this was something that we used last time as well. So the fixed point of phi of omega comma n, I denoted by x star of omega n. It's going to depend on omega and n, possibly. In Barnsley, any such point is called a periodic point of the iterative function system W. This is not standard notation or standard terminology as far as I'm concerned, but it might be good to think about it that way. So let's try to sort of understand this Hutchinson coding theorem and how you can use this, or why is it is useful and so on, using this Sierpinski game. So here's an iterated function system. We had looked at this before. Of course, this generates the one version of the Sierpinski gasket. My space, capital X, is R2, so the plane, and I have 3 contractions. And in fact, there are similitudes. That is to say, given any 2 points, each of these functions contract the distance between these 2 points by 1/2, or by 2. Okay, so the unique fixed point of this is the origin, of course. What is the unique fixed point of this? It's a contraction, so it has to have a unique fixed point.
1, 0.
Yeah, right. So you plug in 1, 0, you just eyeball it. You can apply this, iterative algorithm as well, but in this case, the functions are not that complicated, so you can just test things out. So if you were to plug in 1, 0, this would be 1 plus 1 divided by 2, and this is 1, comma 0. So the fixed point of W2 is going to be 1, 0. And by essentially the same argument, the fixed point of W3 is going to be 0, 1. Now, by this property, certainly these 3 points must be in the attractor. We know, we have seen this, that the unique attractor for this iterated function system is a sphere Pinski. But this is sort of like a different perspective, perhaps. So these are, they have to be in A sub W. Now, this statement doesn't say that A sub W is only these 3 points. Because you see, so far, I've only looked at sort of the cocycle at time 1. So I looked at this. But in this union, you have to take an arbitrary time, which means that not only do you need to look at the fixed points of these 3 functions, but for instance, you need to look at the fixed point of W1 composed with W2. That's going to give you possibly a different fixed point, and so on. It's still a contraction, but its fixed point is different. So what this is saying, this statement that I've boxed in orange, is that using such fixed points of arbitrary compositions of contractions given in your iterated function system, you can approximate any point in the attractor arbitrarily well. Okay. So here are the 3 fixed points that we have already, and then you're going to have more, right? So W1 takes this and turns it into this. Inside is included, of course. But I'm not going to draw it because otherwise it's not going to be seen. And then this is W2. Sorry, this is W3, and this is W2. So. Sierpinski game is this. You start at any point in this triangle, okay? But you want to choose a point so that based on a certain algorithm, you want to stay inside the triangle as long as possible. And the algorithm is this. Given the point, let's say you choose this point over here. You look at these 3 corners. You find the corner that the point that you chose is closest to. Okay? So in this case, I chose it here, and I know that by looking at it, I can see that the corner that is the vertex that is closest to the point that I chose is this one. So you find this point, and then you kick your point that you chose by doubling the distance that you see here. So if this is this distance, and then you want to apply it, so it goes somewhere here. Okay, so you started here, time 1, now you're here. Okay, so you landed somewhere here, which means that in the next iteration of the algorithm, this is the closest point that you have to sort of kick from. So you look at this distance, you double this distance, so you're going to land somewhere here, and so on. And then it's going to be here. So it looks like it's going to land somewhere here, actually. Okay. I can still look at what is the largest point, or closest point, and it's over here. When you kick it out, you're done, right? So I started here, 1, 2, 3, 4. In 4 steps, I was able to, I escaped the Sierpinski gasket, or I escaped the triangle. The aim of the game is to stay inside the triangle as long as you want. Okay, so you want to maximize. You don't want to escape. You want to stay in, because if you can stay in, you can keep playing, basically. Now, these fixed points are, in a sense, sort of the easy choices for the initial condition you can make. Okay, so before I go into that, is this sort of idea clear? Okay. So you can sort of like trick or use a trick, of course, and you can say, oh, this is I'm going to start here. Okay. So what happens if I start here? This is my initial condition. The closest point is this, which means I need to double the distance from it. Okay, so the distance is 0, so I'm going to stay here. Okay, so that's you cheated in a sense. You started with a fixed point and you're not going anywhere. Is this sort of like clear? So let's look at a period 2 in Barnesi's terminology point. So I don't want a fixed point, so I'm not allowed to use any one of these corners, but let's try to find some other point. Well, for instance, if I were to take a point in this boundary, I think I can just keep bouncing between these 2 points. Okay, so let's say this is 1/2. So if I were to have sort of x comma 0 here, let's say that x is like this, well, the point that is the corner that is closest to the initial condition is this point, which means I need to double this, which means now it's going to be 2x. Okay, so what I want is
2x equal 1 minus x.
Say again?
You want 2x equal 1 minus x.
Is that what I want? Maybe. Let's try it. This is what you're saying? Okay, so x is, what is this? 1/3? Let's try this. If x, so if I had chosen 1/3 here, what happens? 1/3 comma 0. Now I'm going to double it. I'm kicking it this way. Okay. Now it becomes 2/3 comma 0. Now the closest point, I think you're right. The closest point is this point, which means in the next iteration, you're going to push it that way. So when you're pushing the point, you're always pushing along the same line. So if you're pushing from here, you look at the line between these 2 things. You should sort of like draw the ray and push that way. So if you're here, okay, so if you push this in this direction, so this is x, t, let's say. Now this is going to be 2t, which means that you're going to take 1 minus t and send it to 1 minus 2t. Okay, so if this is 2/3, t is 1/3, which means that this expression is 1 minus 2/3, which is 1/3. Okay, this is what happens. Okay, so you can sort of like keep bouncing between the 2 things. So you get to stay, you get to win the Sierpinski game again. You can keep playing for infinite time, and you're never falling out of the triangle. Now, let's say, okay, that's again cheating because it's on the boundary and stuff like that. Let's say that you're not allowed to choose any point, none of these vertices and none of these edges. You need to choose a point that is inside. How do you do that? Okay. Now this is perhaps where this idea of the coding starts to sort of become useful a little bit. Now, you can sort of like try to eyeball this and so on. But the problem is that because you're, heuristically speaking, because you're always increasing distances by 2 from certain points, if you're not very careful, you're going to come up with a point that is not good, okay? So you want to come up with an actually good point. So the way to do this, or one way to do this, is to actually use the coding. Okay, so what is the coding in this situation? This capital phi function. Let me just delete this. So capital N in our notation is 3. I have 3 iterated functions, 3 contractions. So my shift space is a shift. If it's a space consisting of all those sequences that has as entries 1, 2, or 3. Oh. So instead of trying to find a point like this, find a nice sequence that works, and then use your coding map to obtain a point. And of course, it's going to be in the attractor, but the attractor is going to be a subset of this triangle. Okay. So instead of looking at an x, a and x, look at a nice omega. So find a nice omega. Then choose x comma y as phi of omega. Okay. Okay, I might mess this up actually. So I want something like this. Maybe maybe I want to choose a point over here, perhaps. I feel like I'm going to mess this up. So ultimately what I want is this too. It's like such that xy is not in the boundary of the triangle. Now, what does that mean? How could an omega, any sequence, land on the boundary? So in order to get this particular point, for instance, my sequence would be 1, 1, 1, 1, 1, 1. Okay? So because the moment I say the first entry of omega is 1, by definition, I know that it has to land somewhere here. Then I can choose, oh, the second entry is 2, in which case now I know that it's in this triangle. And then I can say, oh, the third entry is 3. Okay, so now it's in this smaller triangle and so on. Maybe I should leave that as an exercise, actually. I did this a while ago, but I don't want to confuse you. That's an exercise. Find a nice point. Find a periodic point if you want, or find a non-periodic point if you want. Okay. So ultimately, the point is to use the sequence space, because finding periodic points in sequence space is rather straightforward. You can come up with arbitrarily, well, let's say you can find points that are periodic with arbitrarily large periods by just taking different terms in your sequence. Okay. Any questions about this? I know I didn't do a very good job here, but I should have prepared this before. Okay. We have a couple minutes. I want to say a couple things. Okay. Let's do this. So if the B-IFS is totally disconnected, I call that this was one of the three properties, three different iterated function systems you could have, which means that if you have two distinct indices, then their images are different, or in fact, they are not intersecting. So for instance, the Pinski doesn't satisfy this property because the intersections, there are intersections, but the Cantor set, the standard Cantor set, does satisfy this. Then the coding map phi from the shift space to the attractor in fact becomes a homeomorphism. In fact, these are equivalent. In which case, one can define a certain intrinsic dynamical system on the attractor, and that is the dynamical system associated to the iterated function system. So we have this diagram. I want a function here so that phi becomes a conjugacy between this function and shift. And how do I define this? Well, in this case, phi is it's a homeomorphism, which means that I can invert it. So I can define f to be, so I want it to go this way. So it's going to be phi inverse sigma phi. Sigma phi inverse. So this is a dynamical system. It's iterates of one function on this attractor. And so this is the intrinsic dynamical system associated to the iterated function system W. And really this Sierpinski game, this algorithm that we were discussing, is literally this function, applying this function. One thing I didn't say was this algorithm is not exactly well-defined all the time, because there are certain points on the triangle that are equidistant to certain points. There's a certain barycenter if you want. In which case it does not actually define this function, this algorithm that we were discussing. But in case you have your iterated function system totally disconnected, it's perfectly fine. Okay? Now, one perhaps important example, and this is probably what we're going to end with today, is, well, iterated function systems on shift spaces themselves. This is kind of like a confusing thing to think about, but it's still useful. After all, I started with an arbitrary B-IFS on a complete metric space X. There's nothing that's stopping me from choosing that metric space to be a shift space to begin with. Okay? So let's say that X is the shift space. Maybe I should write it like this. Let's say 1 to n. Okay, for any I from 1 to n, I can define this function w sub I. It's going to be on X, the shift space still, but and how does this operate? Well, you see, even though it is a shift space, I'm still using lowercase x, just so that I have sort of different contexts here. Well, how does this going to operate? Well, it's going to do this. It's going to be sort of like the opposite of the shift that we were using before. Instead of moving to the left, it's going to move to the right and then put this entry inside in that entry, in that empty spot. That is to say, if x is x0, x1, x2, dot, 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 applying wi corresponds to taking these terms, moving all of them to the right by 1 unit, and then you have now an empty space. Put into that empty space this I that you chose. Okay? Now, I'm going to leave that as an exercise to verify that each of these are contractions. Which means that if I were to take all of them, I have a B-IFS, which is like a standard B-IFS if you want, acting on shift space. So this is acting on X is a B-IFS. And furthermore, in this case, we have again coding, and that's going to be the last thing I'm going to say today. Phi, this Hutchinson coding, it's an exercise, which is very good, is that Hutchinson coding, in this case, is going to be nothing but the identity function. So you get to code the shift space by itself, by not doing anything. It's kind of bizarre to say this, but in math you have to include these kind of situations. Okay? These are nice exercises. Next time we're going to discuss a little bit more as to how one can use this. Okay? Thank you. Have a nice weekend.